can see how many people
Oh yeah.
are watching.
If any.
Zero's a number.
And I always have to remember to mute the YouTube, otherwise everything comes around twice. Okay. One watching now. I don't know how they did that. I think they make those numbers up. Okay.
Could that be you?
Yes, that would be me. Yes, it's counting myself. So actually, that's a good point. We should subtract 2 from our number last time, right? Because that was, you were watching and I was watching.
Fair enough. Good point. Yep.
But where do I put this? Here. Okay. Although, you know what? It says 1 viewer at the bottom of the Hangouts feed, so I wonder if that's the same thing. Oh, hey. Daniel, hi. Great.
Oh, I see an icon of somebody.
Yeah. Anyway, I wrote to the people who are helping organize the various groups, and they sent me feedback about how their groups went. So I'm going to write a blog post about that.
Oh, about how, you mean just how the discussions went?
Yeah, exactly. So
like how they went, or
yeah.
what they thought? Like
no, not just how they went.
Right. I mean, I'm interested in both. But.
Yeah, summarizing what a lot of people thought seems like a lot of work. So no, I'm just the logistics of the groups.
Yeah.
So one of the groups like didn't work, and another one, or I shouldn't say it didn't work. It gradually disbanded, and another group was done in person.
No, it's not.
It was really big, and it had a very different dynamic, it sounds like, than the other ones.
Thanks.
Hey, Dan, can you hear us?
Hey, I can hear you guys. Can you hear me?
Yeah, for
Indeed.
sure.
Awesome. But no video, I guess, but that's fine.
Oh, okay. Well, we just don't have your video.
Yeah, I can see you guys. I can see you guys great. So you don't have to see me.
Okay, no worries.
There's
well, yeah, hopefully. I know a few folks from, okay, good. I know a few other folks from our group wanted to join today.
Yeah, that'd be great. So
someone else just joined.
Yeah, we scheduled these specifically at times that other people like normally meet because we thought maybe that would be helpful.
Yeah, absolutely.
Hey, Chris.
I see a Christopher.
Hello.
Hey.
Hello.
Nice to meet all of you.
Yeah, indeed.
Well, I'm declaring for a quorum. I think we should start.
Let's do it.
That sounds great.
Okay, I'll just throw out the first question so nobody feels pressured to do that. I like the question about the story of the book. So let's see, this is okay, what is the story behind the book? How did you come to write it? And how did you reconcile having diverse audiences? We know that there's a lot of emphasis on the pedagogical value of your theory, and why did you frame the book the way you did?
Yeah, so I mean, there's a story. The book is quite transparently an expansion of the 2010 paper, and so we can either, you want to know the story behind the paper and then behind the book, or just behind the book post the paper, or whatever, or either way.
Yeah, give us the full story.
The full story. So I mean, the story behind the core idea that formed the paper and then eventually the book is that there were a number of different ways in which the parallels between population genetics and community ecology came to my attention. So as a master's student, I had co-supervisors who had both ecological and evolutionary perspectives. As a PhD student, I had co-supervisors, one ecologist, one sort of evolutionary ecologist. So the two sort of bodies of theory were always, commingling in the various discussion groups I was part of. And then Hubble's book, which everybody knows about, is a very explicit importation of population genetics into community ecology. He stresses in his book how he essentially sort of rediscovered some of those models. But it's not just using the analogy. The actual models are exactly the same, and the only thing missing there is selection. And then there are some other authors who have noted these parallels between population genetics and community ecology, but never really, fully developed them. And so, having worked for a while on sort of certain hypotheses that flow out of those parallels, so are species diversity and genetic diversity correlated, which sort of took on a life of its own to some degree, but which maybe wasn't as successful as I thought it might be. It occurred to me that the other main advance you might make by thinking about those parallels is at a theoretical level, importing ideas from one field into another. And since population genetics looks very clean and tidy, and community ecology looks very untidy, it seemed like bringing things over to community ecology would be worth trying. And so that was the story behind writing that paper. And then the book was a matter of, some years later, I got lots of encouragement from people who'd read that paper to do more, basically, write a book about it. And that's always, good motivation when at least you have 5 other people that would read it if you wrote it. And going on sabbatical, I needed a project. And so, the time was right. The paper had been around long enough. I had this encouragement. A publisher was keen, and so I decided to go for it. There was another part of the question about reconciling audiences, or I don't know if anybody has questions on the first part, we can talk about that, or I can also address that one.
Yeah, I think, well, I don't have any questions on the first part. Does anyone else?
No, sounds great.
Okay,
Yeah.
So in writing the book.
I mean, how to reconcile audiences, like, if for someone who's already written, I don't know, 5 books, they have some, experience to guide them, but all you can really do is, try your best, right? So you don't want to. It's one of the fundamental challenges in teaching, and writing a book is in some senses an exercise in teaching to keep the. So if you take the example of a classroom, you have some students that have lots of background knowledge and are extremely hardworking and extremely keen, and then some that have less background knowledge and it takes longer to grasp things. And so you don't want to lose the people at one end by being too challenging or assuming a high level of knowledge, nor do you want to bore the people who already have the background knowledge. So you try to find the balance somehow. If I were to try to have tipped it in any direction, it would have been towards, like a starting grad student. And if that meant that, a senior researcher who's an expert felt, good morning, Daijiang.
Hey, good morning. Sorry I'm late.
That's okay. So if I'd rather have a senior expert researcher, flipping through pages because they know it already, than have a starting grad student simply close it because it's just too advanced. So you do your best, and then you hope it works. But there wasn't much more method to it than that. I suppose having taught both undergrads and grad students and done lots of chatting with other scientists itself provides some guide as to how you might do that, because you start to learn what engages people at different levels, and you just do your best.
All right. So I would encourage everyone to mute their microphone when you're not speaking, and that way we'll minimize the feedback. But right now, don't mute your microphone because I want one of you to ask a question. Do any of you have anything that came up in your group that you thought was unresolved, or anything that bothered you about the book that you want to ask about?
Don't be shy. Don't be shy. I have a very thick skin.
Okay, well, this isn't definitely a criticism, but it is something that I am interested in. So having worked on species-area relationships, you mentioned this a bit in your section on ecological drift and dispersal, And one of the questions that folks have always framed, maybe they didn't call it drift, but they were talking about a sampling effect. So simply that like diversity is limited by numbers of individuals. If we only have one individual, I only have one species. And then as I increase the number of individuals I've sampled, then just by random chance, I'm going to be gaining species. So in other words, I don't need to know competitive effects. I don't need to know any of these other processes until maybe I get to a large enough scale where those other processes start to operate. Now yeah, I guess like from a process perspective, it's different than what drift is, but it seems like it has there's some similar conceptual analogs there. And I wondered if you thought a little bit about that. And if we actually know maybe more about drift than we think we do because we've studied these sampling effects for so long.
Yeah, okay, I'm just making sure my microphone was not muted. I think that's a great question, and I was actually thinking about this the other day because in my class I was teaching, we were talking about species area relationships, and there's certainly some conceptual similarities between, like, sort of pure sampling and drift. There is, I think, an important distinction, because so you can often, especially if you study mobile animals like insects, you catch them in a trap, and then almost everybody uses, or it's very frequent to use rarefaction to estimate diversity from those samples. And when you do that, you have this individual accumulation curve. And so you can imagine the same thing where you have, plankton that are pretty well mixed in some body of water. And so as you sample them, you have 10 individuals, and maybe you have 10 species. But those 10 individuals don't really form any kind of unit to speak of, really. And so they aren't a community. Even by the very loose definition that I use in the book, which is a set of species that live that live together in a particular place and time. Those first 10 individuals that you get as you accumulate them don't form any sort of unit of that nature. Now, it's a bit different when you have sessile organisms, because if you're starting to accumulate plots, so how many species do I have in one plot, and then 2 meter squared plots together, and so on, those are actually like little spatial units. And so they're actually the sampling and the types of effect you'd expect via drift, I think, start to converge. But simply to say that, like, people always use sort of the example of just scattering jelly beans randomly on the floor, and if you put down a 1 meter squared quadrat, there'll be fewer colors than in a bigger one. To some extent, that's just trying to think now. See, but there's no, like, that happens, like, regardless of any sort of demographic effect, because drift at some level is due to demographic stochasticity. So it's, yeah, I mean, I suppose I don't really have a very clear answer. I mean, what are your thoughts on it?
I've also struggled a little bit talking in the group, because at one hand we thought, well, maybe drift only really applies when we're talking about these little isolated islands, and that's where numbers of individuals is inherently low. We know things aren't dispersing in or leaving, and so if we see species plink out of those small islands, then, and presumably if it's a homogeneous area, under some assumptions, that would be a real drift type effect that really fits with our model of what drift is. But what got me thinking more about this was last week when we were chatting, you mentioned, like, the fact that you have an integer is so important to that individuals must be integers, and that you can't have partial individuals. That idea is so critical to, like, those rarefaction curves and making predictions about how many species you're going to get. And so there's definitely some similarities. For me, I tend to think of the sampling method as capturing a process-free component, of community assembly. I tend to think of the neutral theory with no dispersal limitation, just ecological equivalence. I tend to think of that as a sampling effect type of model. So I lean more towards saying these can be treated as the same. But I can see your point that the way drift is conceived, at least, it doesn't necessarily apply. You know, sampling, you can build lots of things into sampling, lots of ecology into sampling effects. Like you can have aggregated sampling, or you're drawing from not just a complete Poisson distribution, but a negative binomial distribution in terms of occupancy. Suddenly that changes the pattern you're likely to get. Have you brought in biology? When you did that, is it no longer ecological equivalence? I don't know. It's a kind of a philosophical question about how drawing from different distributions maybe gets you different bits of biology. So.
Yeah, no, I think those are all good points. I wish I would love to have had a more satisfying, profound answer to the question. And but I think that just purely, you know, sampling more individuals, getting more things, you know, it's hard to ascribe a lot of biological relevance to that, even when it comes to drift. Again, when you get to sort of sessile things and you have spatial structure, you can ask, like, if organisms were you know, distributed spatially randomly, you'd get a certain accumulation of species as you move through space, and that can actually deviate from what you actually see. Because if there's spatial structure, you'll tend to accumulate things more slowly than you would if they were totally random. So so you can look for deviations from that.
So that sounds
as well.
cool. So that would suggest then, if you had a given set of those individual based samples you were talking about with the insects, let's say instead of spatial structure, we're thinking of temporal structure. You could say, like, here's my observed rarefaction. Here's, you know, which would necessarily be accumulating species more slowly because of theoretically things are temporally autocorrelated, right? And then you could also, from that data set, construct well, here's what I'd expect if things were just totally random. That could be the drift expectation, I guess, or sampling only expectation. And that might actually let you to, I guess, quantify how strong is this sampling only component in your data set. Or drift only component. I mean, it would certainly probably be pretty important in certain contexts.
Well, you can, yeah, the fear though, so you can, it's easy enough to quantify a deviation from it, and people have done things like that. The question is, if the accumulation looks exactly as the random one does, you know, can you conclude that therefore it was actually produced via randomness? Because there's always the possibility that you know, deterministic processes, selection processes of some sort, that just kind of cancel each other out and then look random. That's something that people always worry about. Does the resemblance between a null or neutral model and nature imply that in fact that pattern was created by the null or neutral process? And so you have to sort of believe firmly in the kind of Occam's razor philosophy that whatever your simplest explanation is the one that you should go with in order to make that link in a strong way. But the resemblance of a model and data does not in and of itself imply that that the model is the right descriptor for how the data were generated.
I completely agree, and unless someone has another question, I think that could be a good jumping off point for other things. Dejing, did you have a question you wanted to insert there?
No, I just like a slightly different question. So you're talking about sampling effects and the species error distribution. But like, say, if you use species list of, say, the state or the state of US, then that problem probably is not a big issue, right? So.
You mean when you have a very large?
Yeah. So for example, like the species list of every state of the United States, you probably get a pretty good estimate for that.
A pretty good estimate of what? I'm not completely following.
Oh, the species list of every state.
Yeah.
I think he's asking if the species area curve, like accumulating states, would also reflect sampling effects.
Oh, you mean once you've got like a huge number of individuals, like, you know, so if you're accumulating tree species across the states, you've already got 1 billion trees in,
sure.
you know, Arkansas, and so Is it,
or
does it
even
really,
just like from many people, like they contribute to the list. Like when you see a new species, you add to the list. Like over like 100 or 200 years, you probably get a very good like list of the species you observe.
so you're saying that you feel like you've gotten to the asymptote of your sampling
Yeah.
curve?
Yeah.
It sure seems likely. I mean, it does depend on your scale. Like I feel like I've seen these studies recently where, you know, sometimes county level, for example, you know, diversity is strongly correlated with like the presence of a university and botanists, you know. So it's like, you know, even at a scale like that, you know, in certain places there aren't that many people looking and noting the new plant species, and so the list might be shorter. And it's a comparable type of thing. It is sort of a sampling. Like people have looked more in certain places, and therefore it looks like there's more things.
Yeah, the reason I'm asking is that I'm compiling a data set to look at the National Park Service of the United States. So basically, you can get the species list of every units covered by the NPS, the National Park Service, and also at the same time, you can get the area of each unit, and you can get all the environmental variables such as climate or visitors. They are publicly available. So so I'm thinking, so the main question I'm going to ask is like, what is the species area relationship for native and exotic species for plants and birds? And also, what about the phylogenetic diversity for the native and exotic? And also, I noticed in your book you asked whether the area actually affect the beta diversity. You know, so that's kind of some very interesting question. I probably can use the same data set to ask. Do you have any suggestions for this project?
Oh, well, so I mean, I'm somewhat familiar with the kinds of data you get from, you know, lists of species in parks.
Yeah.
And certainly when it comes to the abundances of the common things, I definitely trust data of that nature. When it comes to the actual lists, I think there can be a huge effect of just how thorough the survey was and how much of an expert. So I can't comment on the birds, but let's say for the plants, you know, how expert was that botanist? You know, so there's a guy in Quebec named Jeffrey Hall who's like, top botanist, right? And so if you pay him to spend 2 months surveying your park, you're going to get a longer list than if you ask me to do it, and like considerably longer. And he's done some places, right? And so I'd worry a little bit about interpreting, you know, especially like how many species are in that tail of rare things, which makes up a lot of the diversity when you compare multiple parks like that. But yeah, certainly when it comes to, you know, the composition, I think they're far more comparable. So I just wanted to note a couple things that when you have ideas getting thrown out, it's here to lose things. But I made a note of a couple things that relates to this, and it came from Dan's question. And so one, you know, was the question about whether or not drift might be only important on, you know, just like some really small isolated island. And so, I mean, certainly even from population genetics, you know, population size and community ecology, the community size is the key, you know, variable that informs you as to the likely importance of drift. And if it's really, really large, you know, if J is huge, then you don't really expect a very large effect of drift. And even in population genetics, you know, like Fisher and Wright argued for a long time, not so much about models. They've kind of agreed on the structure of the models, but they argued about just how often in nature was population size small enough to really make a difference. And so that's an empirical question. It's not one that I have an opinion on how important it is. Is it in real ecological communities? But it seems certain that it can be important often enough that you can't ignore it from the outset. So the other point had to do with, so we keep talking about richness and how it depends on these accumulation curves, but some aspects of diversity don't depend on those accumulation curves. So if you want to talk about like just let's say like body size variance of the insects in your community. As soon as you have 2 insects, you have an unbiased estimate of the variance of that trait. It's hugely, you have a huge standard error on that estimate of the variance because you only have 2 insects. But there's no, if they're random samples, increasing the sample size gets you a more precise estimate of the thing you're looking for, but it's not a systematically biased one. And so there are other sort of attributes of a community for which that pure sampling effect shouldn't really be much of an issue if one desired to sort of either get rid of it or study something for which it wasn't going to be a big deal.
Cool. So I guess on like a kind of a preliminary results is for the native plant species, there's like a very strong like area species richness relationship, but not as strong for the exotic. Instead, the exotic they have very strong relationship with the visitors, the number of visitors per park. But the visitor and the area of parks are not correlated at all. So that's very interesting.
Yeah, I agree, and certainly, if I were to phrase things in terms of, like high-level processes, then dispersal variance in dispersal among these parks is likely the key to explaining the exotic richness. Why you get a species area relationship for natives, as we all know, has multiple explanations or probably multiple factors acting at once. But no, that's quite interesting. So at least at the moment, the dispersal effect is outweighing any other effects on non-native diversity in those parks. That's cool.
So Mark, you brought up, I think, a really great point there earlier when we were talking about drift and sampling effect, which was kind of more of like a philosophy of science. We see a lot of community ecologists comparing patterns they observe in nature to like a randomization, right? Where here's what I would expect if I just shuffled the data. And you brought up the point, well, that doesn't necessarily mean it's process free. These processes could be canceling one another out. Like that's the underlying theory behind like John Hart's maximum entropy theory, for example, is that there's all these processes, but when you aggregate this information down to something like a species abundance distribution, if those processes are even driving, they don't really have a noticeable detect beyond what you would expect just simply due to chance. I think that's underappreciated. But then, so what's the alternative approach? These neutral type models or process type models, which involve us either estimating a lot of parameters and trying to kind of match up and saying, well, here's where we think we are in parameter space based on observed data. So it really kind of says, it's much more of a complex kind of touchy-feely approach in a way, because it's not as clean. It's no longer like a frequentist, yeah, there's process. Versus not, because we've rejected this null model. So I guess I see those as 2 different kind of somewhat competing philosophies. Which do you think maybe is going to be the way forward? And kind of as a follow-up, I noticed throughout your book when you looked at support, you primarily used empirical data. Maybe that, I think, instead of, for example, the fit of a neutral model, for example, to a pattern. Was that, or does that just kind of reflect your own biases being, as an empiricist?
Can I ask you just to like concisely summarize? You said there's sort of 2 options.
Yeah, sorry. That was a long one. So maybe the easier question to answer is the first one, which is, it seemed like in your book, you primarily drew on like empirical, like experimental evidence. If you were going to look at the importance of competition, or if you're going to look at the importance of dispersal, you would go to, well, here's an experiment where we have this versus this. An alternative approach would be like, well, we developed a model where it has these assumptions, it fits the data really well. Or if we ignore this process, it totally fails. I didn't see very many examples like that. And I wondered if that was really intentional, because you feel like empirical data is just so much cleaner to interpret, or really you don't fundamentally trust these simulation data's approaches? I mean, I know last week you said if we're going to look at all of these processes simultaneously, it's going to have to involve some kind of simulation approach. So I guess I'm getting your thoughts on, if we're going to make progress, does it have to be really from an empirical standpoint or model, or those both play a role, and what is that role?
So just to clarify, I think that when you're using the word empirical, what you mean is experimental.
I'm sorry. Yes, experimental.
Yeah. So empirical is like
control kind of approach.
Yeah, empirical is like all the data we collect, observational or experimental. And so,
yeah,
yeah. I mean, in thinking about those empirical chapters, I do believe that there is quite a lot of data that is both observational and experimental. And it is true that for a given prediction, so you have a hypothesis and then a prediction, and most of them are quite targeted, so it's, X, there should be a relationship between X and Y. And so I certainly believe, when it comes to doing the science, I'm definitely like a pluralist in the sense that, all of the different ways of doing it have validity, and certainly combining them is almost always more powerful than relying solely on one particular method. Experiments have the advantage of explicitly controlling for confounding factors. So if you want to know if dispersal increases diversity, you can hold everything else constant, or at least randomize it across, whatever the potentially confounding factors are, and then you add seeds, and then you see what happened. But of course, I think I was also quite clear about describing the limitations of experiments as well. I always have this discomfort with experiments sometimes, in that it's hard to know to what degree they're reflecting what's actually happening in nature. So you do something and it's meant to mimic some natural thing, or maybe it's not even meant to mimic, and then you draw inferences about nature, and that translation can be quite difficult. So I think that the particular type of study that is underrepresented, and I think you're right about this, is definitely certainly on the neutral side, where people said, okay, the neutral model predicts this shape of a relative abundance distribution. Is that what we actually see in nature? And to my eye, those have been revealed as exceedingly weak tests of neutral theory, in the sense that they in no way tell you that selection isn't involved. So you had these papers where, kind of community dynamics were simulated, and if it's purely neutral, you get this shape of relative abundance distribution. And then if you add different kinds of selection, whether it's negative frequency dependent selection or what have you, what do you know? The same shape pops out. And so what it tells you is that the shape of that distribution doesn't really allow you to discriminate what the underlying processes are driving community dynamics. I have a short note about that at the beginning of the neutral section, about how I won't use evidence of that nature in support of neutral theory. So that in that one particular example, that probably explains why we don't see a whole lot of that. But elsewhere, there's quite a few observational examples whereby, if spatially variable selection is important, you should see a relationship between environmental heterogeneity and diversity. And that can be whether you just go looking for it in observational data in nature, or whether you try to do it experimentally. So I think both the observational and experimental are fairly well balanced, and that there is that certain type of evidence, especially for neutral theory, that was not really considered for the reasons I just described.
All right, I just want to
I agree.
ask if Chris has any questions.
I have. I wrote one of my questions down that were answered last time in the video about scale, and I do have a question that is a little bit out there. So I was going to wait.
No, let's go out there now.
Okay. Maybe I won't ask it in all of its radical glory, but my question, I guess, generally is how far can the analogy to population genetics be extended? I found myself oftentimes going back to thinking about the power, predictive value, quantitative mathematical models of population genetics, Hardy-Weinberg, and so on, and how that really gives population genetics its strength. I think that like the Hardy-Weinberg equilibrium, for instance, like that's something that I sort of was thinking about throughout this entire thing. What would be the equivalent of that with respect to what you had written about? And I think about even just some of the assumptions, you know, that's in that. Like there's an infinite population size. And so if you don't have an infinite population size, then drift will always be present. I sort of use those, you know, deductions when reading through this and thinking, so even with respect to the little bit of the discussion earlier, that like ecological drift must therefore always be present as long as we have finite population sizes. So I was just, yeah, I guess in general, it was just how far can this analogy be extended? Is there hopes, do you think, for a more, like borrowing more of the quantitative aspect of population genetics to bring into something like this, maybe sometime down the road?
Yeah, so so that's not out there as a question anyway. It's good. It's a good question. The there's a few different elements to it. So how far can the analogy be extended? So one of the, as I first developed these ideas, you know, some years ago when I was chatting with people about them, you know, a common type of conversation would involve somebody pointing out the ways in which speciation is not like mutation, for example. And so what I realized was that it's not worth attempting to make all of the analogies, you know, precise. So the point isn't that speciation is just like mutation. In a Hubble neutron model, it is. He models it that way. In nature, of course, it is not. But the point is that what you need to round out a comprehensive set of processes that can explain dynamics in a community is some sort of process that creates new things. In this case, it's speciation, and the fact that, you know, it acts in a mathematically different way than mutation is okay. So what I'm trying to say by that is that some of the details of the analogies, I think one has to accept that it's not simply not the same. And it's not even a matter of accepting, it's just recognizing that they're not exactly the same, but the four kind of categories as necessary in a theory of that nature remain. So that's sort of one answer to that particular element of the question. You know, so what gives population genetics its strength? You mentioned that as well, and that I think one of the main things that gives population genetics its strength is the presence in genomes of stretches of DNA that code for nothing. So the fact is you have an internal neutral benchmark in a population. You know, so you have all these alleles that are not under selection. And so that they tell you, they give you the benchmark from which to test for selection. And there's and this is like an industry in evolutionary biology using genomic data to test for selection as deviations from what all the neutral markers are showing you. And so you don't even need we should be profoundly jealous because they don't even need a model really. They have data, they have an empirical neutral benchmark from which to test for deviations, whereas we have no such benchmark against which to test for deviations in community structure. We have to build a model, and so we've been building models of that nature. You know, so there's neutral models which are dynamic, and then null models, which sort of randomize the data. And we've been arguing for decades about whether or not we're sort of building in, you know, as Dan said earlier, do some of those null models have stuff in them already that represents the process we're trying to test? And so that to me is one of the things that gives population genetics its strength that we cannot hope to replicate or discover or anything like that. So you also mentioned the Hardy-Weinberg equilibrium, which, you know, the most common sort of implementation of that has to do with, you know, your sort of genotype frequencies based on gene frequencies, which is a very sort of diploid specific issue, and that's an aspect of the analogy that doesn't really transport over. I mean, the other analogy, I always have to remind myself what these things mean, so I just did my quick Wikipedia search on it, and so the theorem states that allele or genotype frequencies should remain constant in the absence of other evolutionary influences. And so, that's as true in ecology as well. So if there's no drift, no dispersal, no selection, and no speciation, then nothing changes. So you can apply it. What you do with it, then, I suppose I'm less certain. Like in a population, if your genotype frequencies deviate from the expectation of sort of random union, if big A and little a are more common than they ought to be based on random mating, well, then either there's non-random mating or there's selection for those. Like there's something going on, and I'm less sure that that there's a direct application in communities for that. I mean, in principle it applies, but things are always changing, so there's always something going on. There's never nothing going on.
Mark, can I just insert real quick?
Of course.
There was a cool paper, I think it was in the early 90s, by Mike Palmer in a really obscure journal.
I know
Folio Geobotanica. Yeah, and so he used the Hardy-Weinberg approach, which it does kind of fit in with, in some ways, his basic idea was communities should always go to species competitive exclusion. In other words, one species, unless any one of these 6 assumptions, very similar analogies to the Hardy-Weinberg type assumptions, are violated. So if a rare species has an advantage, then you shouldn't see competitive exclusion, for example, which would be a selection argument, right? If you have dispersal into the system, which is he doesn't, of course, it's not in terms of the 4 core ideas that you have, but he uses it purely to organize hypotheses, right? So he says, hey, there's over 302 or something crazy number of hypotheses. Each of these evoke different sets of these violations of these assumptions to all lead to coexistence.
Yeah,
I think it'd be so cool. Yeah. You want to fit in something there?
No. If you've got anything to add, please do.
I guess the thing I always thought would be so cool, and I mean, when your kind of approach to this, getting these big processes to find generality, is then to go through all those empirical studies and say, well, this study found support for these violations of these assumptions. Let's get the effect size of that and actually try to take a step back and say, well, which of these assumptions seem to be most violated? Like, is the rare species advantage most important in plants versus these other groups, or at these scales versus these scales? That kind of taking that more, in the context of your theory, it would be like, which of these 4 key assertions is really, I think the difficulty and the reason we haven't done that is it's so tricky to isolate one particular mechanism and then to estimate its importance. We can say it is important, but actually getting a continuous quantitative measure on that really hard. But I think that's cool. So I just was going to point that out.
Yeah. So every time somebody asks a question, like there's all these different juicy little parts to it, right? So so the first was about that Palmer paper, which I know quite well, and I don't actually think that what he proposes is actually analogous to the Hardy-Weinberg equilibrium. So he proposes as the ecological version of the Hardy-Weinberg equilibrium the competitive exclusion principle, which is essentially that what I call constant or directional selection is the baseline expectation. And so it's not the Hardy-Weinberg baseline expectation is that there's nothing happening, whereas his baseline expectation is that there's one particular form of selection that dominates, and it's not an unreasonable starting point. And Gauss's competitive exclusion principle has been used as sort of the foil to coexistence studies and theory for a long time. But the analogy with the Hardy-Weinberg equilibrium is not. What he proposes is not an analogy to Hardy-Weinberg equilibrium, as far as I can tell. now whether, so you know, from there, you know, you mentioned going towards an approach in which we attempt to identify which assumptions have been violated. Let's measure the effect sizes. So on that side, I think I would totally agree. And I also think that, in fact, using my framework implicitly actually does use the, now that I think about it, it implicitly does think of the Hardy-Weinberg equilibrium as the point of departure, because if any of drift, selection, dispersal, or speciation are causing change in a community, then you're going to deviate from that equilibrium, and we can start to measure their effect sizes. So maybe implicitly, it really is there as a, it's sort of like a ghost in the background. You know, a minute ago I said, well, maybe it's not there. Well, maybe it is actually there. And then, you know, I mentioned this last week, but it actually relates to an earlier point about fitting models. So we're joined by Diogo, and Margaret asked people to turn off their microphones, which is an excellent idea. There you go. Thanks. Turn it on when you have a question. So there are some papers where they will try to fit models to empirical data to say, well, just how strong is this, you know, negative frequency dependent selection. So a lot of the papers that Peter Adler and Jonathan Levine and folks in their labs have worked on essentially fit dynamic models to some observational data to say, well, just how strong is that particular form of selection. And that relates to Dan's earlier question about, you know, what to conclude when the model and your data, you know, look alike. And that's a situation in which I suppose it's somewhat more convincing in that it's they needed to add a very specific thing to the model to get it to look like the data. And so there's a more compelling process to pattern, or pattern to process inference there when they fit models to those data. So I think I hit the main parts of that question that I wanted to.
Great. Okay. Hi, Diego. Welcome. Do you have any questions, or do you want to just listen? Hold on. I need to figure out how to unmute you. You need to unmute yourself, it looks like. Okay. We'll let you do that. It's probably up at the top, depending on what device.
Well, he muted himself, so he must know how to unmute himself.
Oh, you asked the question in the Google Doc. Okay. If you just remind us which one it is, then I can read it out.
I think it has his name on it, Margaret.
Oh, okay. Okay. I'll just read the whole thing. So I'm curious about your thoughts on what would be the obvious next steps in the development of a general theory that takes Hubble's neutral theory and includes selection. You mentioned two papers that try to do that, Hegeman and Leroux and Nolan Fagan, but there are other initiatives that take a different approach, like those that use nearly neutral models of population genetics and the integration of equalizing and stabilizing forces. What line of work do you think has more potential to achieve unification of neutral theory and selection?
Yeah, I remember seeing that question before. Thanks for that. It's a good question. It's not one that I have a really strong opinion on, in the sense that the advantage of, I think, adopting the framework that I've proposed is that when people develop any one of these particular approaches to modeling, and really we're talking about different approaches to building models, it becomes easier to be really clear about what your assumptions are. It's easier to declare what your assumptions are with respect to 4 high-level processes than it is with respect to, let's say, the 100 different hypotheses mentioned in that Palmer paper that was mentioned earlier. And so in population genetics, it's also the case, you know, despite a very coherent sort of high-level framework, people model things in quite different ways. And what keeps the whole discipline unified, I think, is that when they do that, it's easy to be pretty explicit about which, you know, form of selection you're going to focus on, whether you're going to assume infinite population size, in which case drift is irrelevant, and if you have finite population size, how is it implemented? And I don't think, so I don't really have an opinion on which particular type of modeling approach will be most suited to achieving unification. I think the adoption of a framework like this has the advantage of allowing any of these approaches to be relatable to one another via their clear statements about what they've assumed and how they've decided to treat a relatively small set of processes. So, in the book, I present these simulation models, and that's not meant to be some sort of indirect way of saying that I think that's the best approach. I decided to use those purely because I thought they were the easiest to understand for somebody who doesn't do modeling. And so, in many of those cases, they could be modeled in different ways. But overall, yeah, I think all these approaches can contribute, and hopefully they can talk to one another a bit more effectively if they were to adopt a framework like this.
Great.
Are you satisfied, Diogo? You can nod. Oh, thanks a lot. There we go.
Let's see. So we've got about 8 more minutes, it looks like. Does anybody else have a question they want to throw out there?
So maybe I will ask a question of you. So obviously ask me questions if there are remaining ones, but if I were to ask one question, you can send me email later if you don't have an answer right away. I mean, people have asked me, like, what sort of research directions does this approach point us to? What should we do next? And as my intro part to the last chapter indicates, I'm not a huge fan of, providing instructions. Okay, here's what I think all of you starting grad students should now do. I threw out some ideas, but I'm really curious whether or not people out there have been, has it led them to a research avenue that they, might not have thought of otherwise. So, in some ways, rather than me being the one to suggest what other people do, I'd love to know what they thought this way of thinking, what directions has it pointed them in, if any at all?
I can start. So for me, I read this pretty much after I've done most of my community ecology. Right now I'm doing ecosystem ecology stuff, but I'm still working on some of my dissertation chapters. And in particular, I have one chapter that uses a long-term data set and is quite complicated and has many potential stories coming out of it. And I really struggled in writing that particular chapter about how to frame it, about how to fit it into the literature. And so for me, because it has a selection component, a drift component, and a dispersal component. And having, that's part of why I really wanted to read the book, is because I was like, I really enjoyed the paper, and it really helped me sort of start thinking about these things. And so for me, although this isn't exactly a future direction, it's a way of making sense of and putting into the context of work that's already been done, an experiment that's already happened that I've been trying to publish and make sense of. So, somebody else can go now.
Yeah, that's cool. I mean, that's interesting in part because I think other frameworks that have been proposed over the years people have found them useful for similar reasons, actually. Like, meta communities is a really good example of a framework that someone read it and said, well, I'm doing that, and so it helped them, I think, frame what was happening already. And I think that happened to some degree with microbial ecologists who've found some use with the framework as well. It was sort of, they had a little more difficulty framing their studies in the context of sort of classic ecological things, competition and predation, because they weren't exactly sure what their organisms were doing. But there was no question there was some kind of selection and drift and dispersal happening that would allow them to frame what they were doing.
I can go next. So I did my PhD on resurvey the Wisconsin pine barrens. So just like some of your work, some of Mark's work. So because that kind of work usually only consider like when you analyze the data, either selection or just like a drift or both, you know. So very few of us consider like dispersal or some like a speciation. I mean, how they contribute to the non-tone changes. And so your book like urged me to consider like what kind of a roles of this dispersal and speciation contribute to the non-tone dynamics. And also more and more I'm trying to use the model-based methods to analyze such kind of data, like basically just fit a model to the data, and how can I like include these 4 processes into the model. Like this makes me like, you know, thinking hard. Although I still don't have some like either clear direction yet.
Well, thanks. That's cool. Yeah. Figuring these things out takes time. That's for sure. They don't happen overnight. But to have stimulated thought about it is a good thing, I hope.
I definitely think, you know, in terms of ways forward, I think the community has kind of realized that we can't simply, if we're going to try to take multifaceted, complex looks at these approaches, we can't just do model fitting routines anymore. You know, that especially with complex models, it kind of, in the end, you're sit there, maybe you have less information than when you began. So I was glad you brought up like the Levine and Adler type approach, where we have maybe empirically estimated demographic parameters that we can say, hey, we trust this number pretty clearly. We're not going to tweak the model a whole lot. What does it say should happen if we, like, for example, take out differences between species? I do think, so more empirical grounding for some of these simulation approaches, I think, can be a useful way forward. Estimate the speciation rate from a phylogeny. See what that tells you. You know, yes, there's a ton of uncertainty around that, but at least that's better than just letting theta, that fundamental biodiversity number, just drift wherever it's going to go. I think that's one useful way forward. I think another useful way forward is, when I go to conferences, it really seems like there's a divide, and this is probably a very old divide, between folks who want to build everything from the bottom up, put in all the details, all the low-level processes, and those folks who want to just start as simple top-down as possible with just one process or maybe something. This framework gives us a way to kind of talk to each other, I think. And I think the progress will be is finding where these predictions meet between those 2 different models, and really understanding in what context do we need this lower, more complex mechanistic, like I think about like mechanistic species distribution models versus a much more correlative, you know, simulation-based approach. What does that mechanism give you? Does it give you better long-term predictions? Maybe your short-term predictions are actually a lot crappier because it's all just autocorrelation. You know, I think about like how do people predict the weather, right? We know that actually predicting the weather has a lot to do with what the weather was yesterday and a lot less to do with all the mechanistic understanding we have. I think as ecologists, we need to be a lot more nuanced and pluralistic, you know, about, well, which approach are we using and under what context, what do we hope to gain from it? I still see, you know, process from pattern is still going to remain a huge bumbling step for us. And in my own writings, I try to be hesitant about inferring process. If I do see that a really simple sampling only kind of fits the data, then that at least gives me some support. Well, maybe I don't need to get more complicated, at least to explain this one pattern. Doesn't mean the processes aren't operating in the community, but at least for the species area curve or the abundance distribution, if I want to know about rare species in my community, maybe, and at least their distribution, not which species are rare, maybe I don't need to know a lot of low-level processes to get at that. So that's kind of where I see progress for ecologists, is to become a little bit more rigorous about how we approach these, really taking these, going from qualitative to predictive science and knowing what's the best approach to do that. So
cool, thanks for that. Yeah, I mean, certainly the first part is very much in line with my own motivation. That is, you know, people who just start from completely different points of departure to attack ecological questions. If there's some framework through which they can communicate or sort of come back to see how one thing relates to another, then I'll certainly be pleased if it can serve that purpose.
Okay, well, we are at the hour, and I was just trying to look up. Ah, here it is. So there's one more chat with Mark that's on Tuesday of next week, November 22nd at noon. If anybody is watching this after it is posted. And thank you all for joining us and asking such great questions. This was a lot of fun. It was really different than the one we had last week. So that was a really interesting thing also. And of course, thank you to Mark for coming and chatting with us and answering questions.
Yeah, thanks to you guys for sure. I mean, definitely when people write syntheses like these, they gain inspiration from the people who provide feedback and sort of read it and make use of it and promote it on the other end. So I appreciate that a lot.
Yeah, thank you.
My pleasure.
Yeah. Thank you,
Thanks
Mark.
a lot, everyone.
For organizing this. This whole thing has been really, really good.
Yeah, thanks,
Awesome.
Margaret.
I'm glad.
Cool. Take care.
Awesome. Take care, guys.
Bye.
Bye.